What if I told you that right now, without a telescope, without any equipment at all, you could see another galaxy with your own eyes? Not a star, not a planet, an entire island of 1 trillion suns suspended in the void 2.5 million light years away. It's there, faint, subtle, a smudge of light just above the northeastern horizon on autumn nights. Most people walk past it their entire lives without knowing. Ancient stargazers saw it too. They just didn't understand what they were looking at. In 964 CE, the Persian astronomer Abd al-Rahman al-Sufi recorded it in his Book of Fixed Stars. He called it a small cloud. Nearly 1,000 years later, Charles Messier cataloged it as M31, not because he found it beautiful, but because he wanted to make sure other comet hunters wouldn't waste time on it. To him, it was a nuisance, a fuzzy patch that didn't move. If you enjoy calm, careful explorations of ideas like this, you might want to like the video and subscribe. It helps the channel continue moving forward. Back then, the prevailing assumption was simple. This object, whatever it was, lived inside the Milky Way. A nearby gas cloud, perhaps, something local and unimportant. But by the early 20th century, doubt started creeping in. Astronomers were split. Some believed the Milky Way was the entire universe. Others thought these spiral nebulae might be distant galaxies, separate from our own. The debate came to a head in 1920, during what's now called the Great Debate. Harlow Shapley argued for a single, all-encompassing Milky Way. Heber Curtis proposed that spiral nebulae were island universes, galaxies in their own right, scattered across a much larger cosmos. Neither side had definitive proof. Then Edwin Hubble stepped in. Using the 100-inch Hooker telescope at Mount Wilson Observatory, the largest telescope in the world at the time, Hubble identified Cepheid variable stars inside Andromeda. These stars pulse with a rhythm tied to their intrinsic brightness, which means you can calculate their distance by watching how they flicker. When Hubble did the math, the answer was staggering. Andromeda wasn't part of the Milky Way, it was 900,000 light-years away. That estimate was later revised upward to about 2.5 million light-years, but the point stood. This wasn't a cloud, it was a galaxy, possibly larger than our own. In one observation, the universe expanded. What had been a cozy, singular cosmos suddenly became an ocean of galaxies, each one a separate world of stars, dust, and mystery. That faint smudge in the sky didn't just survive the scrutiny of science, it shattered our sense of scale. Part 1. What is Andromeda, really? So, what exactly are we looking at when we see that smudge? Messier 31, the Andromeda Galaxy, our closest large galactic neighbor and the biggest member of what astronomers call the local group. A gravitationally bound collection of galaxies that includes the Milky Way, Triangulum, and dozens of smaller dwarf galaxies. Andromeda sits roughly 2.5 million light-years away. That's far enough that the light reaching your eyes tonight left that galaxy before humans learned to make fire, before we were even recognizably us. You're looking back in time, watching a galaxy as it existed in the deep past. And yet, despite that distance, it's visible to the naked eye. That alone is remarkable. Most galaxies are too dim, too far, or too small to see without a telescope, but Andromeda is massive and luminous enough to punch through the darkness. Under a clear, dark sky, away from city lights, it appears as a faint oval glow in the constellation Andromeda. Not sharp, not dramatic, just there. Andromeda is classified as a barred spiral galaxy, the same type as the Milky Way. It has a bright central bulge packed with older, redder stars, some of them billions of years old. Surrounding that core are sweeping spiral arms laced with dust lanes, glowing hydrogen clouds, and pockets of active star formation. There's also a stellar bar running through the center, a subtle structure that helps funnel gas and material inward, feeding the core and sometimes triggering bursts of new stars. At the very heart of Andromeda sits a supermassive black hole. Estimates put its mass somewhere between 110 and 230 million times that of our Sun. For comparison, Sagittarius A star, the black hole at the center of the Milky Way, weighs in at about 4 million solar masses. Andromeda's black hole is a giant, even by galactic standards. The galaxy itself is enormous, depending on how you measure it, whether you're counting just the visible disk or including the extended dark matter halo. Andromeda spans anywhere from 150,000 to 220,000 light-years in diameter. The Milky Way, by contrast, is roughly 100,000 to 130,000 light-years across. Andromeda is noticeably larger. It's also more populous. Current estimates suggest Andromeda contains about 1 trillion stars. That's 2 to 3 times the number in the Milky Way, which hosts somewhere between 100 and 400 billion stars, depending on who you ask. These stars range from massive blue giants burning hot and fast to ancient red dwarfs that have been quietly glowing for billions of years. But Andromeda isn't a pristine, orderly system. Its outer disk is warped. Its halo is streaked with faint stellar streams, long, ghostly ribbons of stars that trace the remnants of smaller galaxies Andromeda has consumed over time. These features are evidence of galactic cannibalism. Andromeda didn't grow this large just by forming stars. It grew by eating its neighbors. And it's still hungry. Andromeda is moving toward us at roughly 110 kilometers per second. That's not orbital drift or random motion. It's a collision course. In about 4 to 5 billion years, the two galaxies will begin their merger, a process that will reshape both beyond recognition. So what is Andromeda? It's a mirror, a parallel to our own galaxy, similar in structure but larger, older, more violent in its history. It's also a preview of our future, a future where the Milky Way no longer exists as a separate entity, but as part of something new. For now, though, it's just a neighbor, close enough to study in detail, far enough that we can see the whole picture at once, something we can't do with our own galaxy from the inside.
Part 2. Anatomy of a Galaxy.
If you point the Hubble Space Telescope at Andromeda's core, something strange appears. The nucleus doesn't look like a single bright point, the way you'd expect from a typical galactic center. Instead, there are 2 distinct bright regions sitting side by side, almost like twin headlights in the dark. At first, astronomers weren't sure what they were seeing. Was this a binary black hole system? Had Andromeda recently merged with another galaxy, leaving behind 2 massive objects locked in orbit? The speculation was reasonable. Binary black holes exist. We've detected them through gravitational waves in distant collisions. But the truth turned out to be stranger and more elegant. Andromeda's core contains 1 supermassive black hole, not 2. What creates the illusion of a double core isn't a second black hole, it's the stars themselves. Surrounding the black hole is a dense cluster of stars moving in highly eccentric orbits. Instead of circling in neat, stable loops, these stars follow elongated elliptical paths. They swing out far from the black hole, then dive back in close before swinging out again. And here's the key. Many of these stars bunch up near the same point in their orbit, specifically at periapsis, the moment when they're closest to the black hole. Because so many stars crowd into that one region at once, it creates a second concentration of light, offset from the true center. It's not a physical structure, it's a gravitational mirage, a stellar traffic jam caused by orbital mechanics. Astronomers call this setup an eccentric nuclear disk. It's rare. Most galaxies don't show this kind of configuration so clearly, which makes Andromeda a valuable case study for understanding how stars behave in the extreme gravitational environment near a supermassive black hole. Beyond the core, there's the stellar bar, an elongated structure stretching a few thousand light-years across the inner galaxy. Bars like this aren't decorative, they're engines. The bar's gravitational influence funnels gas and dust inward from the spiral arms, concentrating material in the central regions. That gas can either feed the black hole directly or trigger new waves of star formation in dense molecular clouds near the nucleus. The central zone is a mix of populations. Older, cooler red stars dominate. Many of them formed billions of years ago during Andromeda's early history. But there are also younger, bluer stars scattered through the region, likely born in more recent bursts of activity. It's a layered environment, like geological strata, each generation of stars preserving a snapshot of the galaxy's past. Understanding Andromeda's core helps scientists model how galaxies evolve, especially those similar to the Milky Way. Our own galaxy has a bar. It has a supermassive black hole surrounded by dense stellar populations. Studying Andromeda gives us a reference point, a way to test theories about galactic structure and dynamics in a system we can observe from the outside. The heart of Andromeda isn't just bright, it's busy, chaotic, and full of motion we're only beginning to map in detail. Part 3. Spirals, Rings, and Stellar Nurseries. Through a backyard telescope, Andromeda looks like a classic spiral galaxy. You can make out the glowing central bulge, maybe catch a hint of the dark dust lanes cutting through the disk. And if the seeing is good, you might glimpse the graceful curve of the spiral arms wrapping around the core. It's a beautiful sight. Clean, elegant, almost textbook. But switch to infrared wavelengths and the structure changes completely. Infrared telescopes like Spitzer revealed something unexpected. Andromeda's spiral arms aren't just spirals. They also appear as a series of nested rings, massive, overlapping loops of stars and dust that circle the galaxy at different radii. These rings are invisible in optical light, hidden beneath the glow of the spiral structure. But in infrared, where cooler dust and older stars shine brighter, the rings emerge clearly. Why does this happen? The leading explanation involves resonances. As stars and gas orbit the galaxy, they interact with the gravitational influence of the central bar and the overall mass distribution of the disk. At certain distances, these interactions create resonance zones, regions where orbital periods sync up in specific ratios. Material gets trapped in these zones, piling up over time and forming ring-like structures. It's a bit like standing waves in a vibrating string. The frequency of the oscillation determines where the peaks and nodes appear. In Andromeda, the bar's rotation and the disk's gravity create similar patterns, sculpting the distribution of stars and gas into rings that wouldn't be obvious from the visible light perspective alone. This isn't unique to Andromeda. Other barred spirals show similar features. But because Andromeda is so close and so large on the sky, we can study these structures in far more detail than in distant galaxies. The spiral arms themselves are active star formation. Young, hot stars, many of them blue giants burning through their fuel at prodigious rates, light up regions of ionized hydrogen gas, creating glowing H2 regions visible even in amateur photographs. These stars don't live long. Within a few million years, they'll explode as supernovae, seeding the surrounding gas with heavy elements and triggering new rounds of starbirth in the shockwaves. Andromeda's star formation rate, however, is surprisingly low for a galaxy of its size. It forms only about 1 solar mass worth of new stars per year. The Milky Way, despite being smaller, forms stars at roughly the same rate or slightly higher. This suggests that Andromeda may be entering a quieter phase of its life, possibly because it's already processed much of its available gas into stars, or because feedback from past star formation and black hole activity has heated or expelled the gas needed to fuel new stellar generations. The dark dust lanes are another striking feature. These are clouds of interstellar dust, tiny grains of silicates, carbon, and ice that absorb and scatter light from background stars. In optical images, they appear as black streaks cutting across the disk. But they're not empty, far from it. These are some of the densest, coldest regions in the galaxy, where molecular hydrogen accumulates and new stars will eventually form. Scattered throughout Andromeda's disk and halo are globular clusters, ancient, tightly packed collections of stars that formed early in the galaxy's history. Andromeda hosts an estimated 450 to 500 globular clusters, compared to about 150 in the Milky Way. Some of these clusters are extremely metal-poor, meaning they contain very few elements heavier than hydrogen and helium. That's a sign of old age. They were born when the universe was younger and less chemically enriched. These clusters act as fossils. By studying their ages, compositions, and orbits, astronomers can reconstruct the early history of Andromeda, when it first formed, how quickly it grew, and what kinds of smaller galaxies it absorbed along the way. The spiral arms, the rings, the dust, the clusters, they all tell pieces of the same story. Andromeda isn't static, it's a dynamic, evolving system shaped by gravity, gas physics, and the violent history of galactic mergers stretching back billions of years.
Part 4. Satellites and the Halo.
Andromeda doesn't float alone in space. It's surrounded by a retinue of smaller galaxies, most of them faint dwarf systems bound to it by gravity. The two most prominent are M32 and M110, both visible in amateur telescopes near Andromeda's core. M32 is a compact elliptical galaxy, dense and bright despite its small size. It sits close to Andromeda's disk, and there's evidence it may have passed through the larger galaxy at some point in the past, stripping away its outer layers and leaving behind only the dense core we see today. M110, also known as NGC 205, is a dwarfed elliptical on the opposite side. It's larger and more diffuse than M32, with signs of recent star formation, unusual for an elliptical galaxy, which are typically dominated by old stars. Beyond these two, Andromeda has at least 14 other known satellite galaxies, though the true number is likely higher. Many of these are incredibly faint, discovered only in deep surveys that can detect the subtle glow of distant stellar populations. Some are so dim they contain only a few thousand stars, held together more by dark matter than by their own stellar mass. These satellites aren't randomly scattered. Observations suggest they may lie along a thin plane, a flattened distribution that cuts through Andromeda's halo. This is unexpected. In standard cosmological models, satellite galaxies should be distributed more or less spherically around their host. The fact that they appear aligned raises questions about how they formed, whether they fell into Andromeda along a preferential direction or whether tidal forces from past interactions shaped their current arrangement. Then there's the halo itself. Andromeda's stellar halo is a vast, diffuse cloud of stars extending far beyond the visible disk. It's faint, so faint that individual stars are nearly impossible to see without sensitive instruments. But deep imaging reveals structure within it: loops, shells, and streams of stars tracing the remnants of smaller galaxies that Andromeda has consumed over billions of years. These stellar streams are like archaeological records. When a small galaxy falls into a larger one, tidal forces stretch it out, pulling stars away from the core and smearing them into long, thin ribbons that wrap around the host galaxy. Over time, these streams fade and disperse, but for millions or even billions of years, they remain visible as ghostly tracers of past mergers. One of the most prominent features is the giant stellar stream, a massive arc of stars looping through Andromeda's halo. It's thought to be the remnant of a dwarf galaxy that fell into Andromeda roughly 2 billion years ago. The stream contains stars with similar ages and compositions, confirming they share a common origin. There are other streams too, some more fragmentary, others still being mapped. Each one tells a story of a galaxy that no longer exists as a separate entity, absorbed into Andromeda's growing mass. This is how large galaxies grow. Not smoothly, not gradually, but through violent encounters, mergers, collisions, tidal stripping. Andromeda's halo is a graveyard of smaller systems, their stars now part of a much larger whole. And surrounding all of this, invisible but essential, is the dark matter halo. We can't see dark matter directly. It doesn't emit, absorb, or reflect light, but we can infer its presence through its gravitational effects. The stars and gas in Andromeda's outer regions move faster than they should if only the visible matter were present. That extra speed requires extra mass that doesn't shine. Current models suggest Andromeda's dark matter halo extends far beyond the visible galaxy, possibly out to several 100,000 light-years or more. This halo outweighs the galaxy's stars and gas combined, making up roughly 80 to 90% of Andromeda's total mass. It's the scaffolding that holds the galaxy together, the invisible architecture that shapes its structure and evolution. The Milky Way has a similar halo, so does every large galaxy we've studied. Dark matter isn't some exotic addition, it's the dominant component of galactic mass, the framework on which galaxies are built. Andromeda's satellites, its stellar streams, its dark matter halo, they're all reminders that galaxies aren't isolated islands. They're part of a larger ecosystem, constantly interacting, merging, and reshaping one another over cosmic timescales. Part 5. Mysteries and Artifacts. Deep astrophotography sometimes reveals features that shouldn't be there. Faint arcs, diffuse filaments, clouds of ionized gas that don't quite fit the expected structure of Andromeda's disk or halo. Some of these features appear in narrowband images, photographs taken through filters that isolate specific wavelengths of light, like hydrogen alpha or oxygen 3 emissions. They show up as ghostly wisps threading through the space around the galaxy. The question is, where do they come from? Some might be extragalactic, genuine structures associated with Andromeda itself, gas expelled from the galaxy through stellar winds or supernova-driven outflows, materials stripped from satellite galaxies during close encounters, or perhaps remnants of ancient star formation events, ionized clouds still glowing faintly millions of years later. But others could be local. The Milky Way has its own interstellar medium, clouds of gas and dust scattered through our galaxy that can appear in the same direction as Andromeda. When you're looking at deep images, you're seeing everything along that line of sight, both foreground and background. Distinguishing between them isn't always straightforward. This is where spectroscopy comes in. By analyzing the light from these features, astronomers can measure their Doppler shift, the slight stretching or compression of wavelengths caused by motion. If a cloud's velocity matches Andromeda's recession speed, the rate at which it's moving toward us, it's likely associated with M31. If the velocity matches the Milky Way's local gas velocities, it's probably foreground contamination. In practice, though, the results aren't always clear. Some features fall into ambiguous zones where the velocities overlap. Others are too faint to get reliable spectroscopic data. We're left with structures we can see but can't definitively place. One example is a set of faint arcs visible in some hydrogen alpha images. They curve outward from Andromeda's disk, extending into the surrounding space. Are they tidal debris from a past merger? Gas blown out by stellar feedback? Or just foreground cirrus clouds in our own galaxy that happen to align with Andromeda? No one's entirely sure yet. There's also the question of high-velocity clouds, compact clumps of neutral hydrogen moving at speeds that don't match the normal rotation of either galaxy. Some of these clouds might be falling into Andromeda, fresh fuel for future star formation. Others could be leftovers from interactions with satellite galaxies, fragments of gas stripped away and left drifting in the halo. These mysteries matter because they offer insight into how galaxies breathe, how they pull in gas, expel it, recycle it over billions of years. Galaxies aren't closed systems. They exchange matter with their surroundings, influenced by tidal interactions, ram pressure from intergalactic gas, and feedback from stars and black holes. Andromeda's environment is more complex than it appears at first glance. What looks like empty space between us and the galaxy is actually filled with diffuse gas, dust, radiation, and the faint echoes of past events we're still trying to decode. Some of these features will eventually be explained. Better instruments, deeper surveys, more precise spectroscopy, all of these will help clarify what we're seeing. But for now, they remain open questions. Cosmic filaments with uncertain origins hanging in the space between certainty and speculation. Part 6. Could we ever visit Andromeda? At 2.5 million light-years away, Andromeda is our closest large galactic neighbor, but close is a relative term in astronomy. Could we ever actually go there? Let's start with current technology. Voyager 1, the fastest human-made object to leave the solar system, is traveling at roughly 17 kilometers per second relative to the Sun. At that speed, it would take approximately 44 billion years to reach Andromeda. For context, the universe itself is only about 13.8 billion years old. Voyager would need more than 3 times the current age of the cosmos just to make the trip. Clearly, that's not going to work. So what if we built something faster? Projects like Breakthrough Starshot have proposed using laser-driven light sails to accelerate tiny probes to a significant fraction of light speed, maybe 10% or even 20% of c. The idea is to fire an array of ground-based lasers at a lightweight sail attached to a small spacecraft, pushing it to velocities far beyond anything chemical rockets could achieve. If we could get a probe up to 10% of light speed, the trip to Andromeda would take about 25 million years. That's still absurdly long, far beyond any practical mission timeline, but at least it's within the realm of geological rather than cosmological timescales. Even then, the challenges are staggering. At those velocities, even tiny particles of interstellar dust become deadly. A grain of sand hitting your probe at 30,000 kilometers per second would release energy equivalent to a small bomb. Shielding becomes a major engineering problem. So does navigation, communication, and the simple fact that any probe we send would be effectively autonomous for the entire journey. No real-time control, no course corrections, just a machine drifting alone through the intergalactic void for millions of years.
What about more exotic propulsion? Fusion drives, antimatter engines, Bussard ramjets. These are all ideas that have been explored theoretically. A fusion rocket could, in principle, reach higher fractions of light speed by fusing hydrogen into helium and expelling the products as exhaust. Antimatter offers even more energy per unit mass, though producing and storing antimatter safely is another problem entirely. Bussard ramjets are particularly interesting. The concept involves using magnetic fields to scoop up hydrogen from the interstellar medium as you travel, fusing it on board for fuel. In theory, this removes the need to carry all your propellant with you, allowing for much longer acceleration phases. But the interstellar medium is incredibly diffuse, only about 1 atom per cubic centimeter in most regions, and the engineering required to capture and compress that gas at high speed is far beyond our current capabilities. And even if we solved all the propulsion issues, time dilation becomes a factor. At relativistic speeds, say 90% of light speed or higher, time aboard the spacecraft would pass more slowly than time on Earth due to special relativity. A crew might experience the journey to Andromeda as lasting only a few thousand years, while millions pass back home. By the time they arrived, Earth's entire civilization could be unrecognizable or gone entirely. So what about shortcuts? Wormholes, warp drives, things that sidestep the light speed limit altogether? The Alcubierre drive is the most famous proposal. It suggests contracting space in front of a spacecraft and expanding it behind, creating a warp bubble that moves faster than light without technically violating relativity. The ship itself doesn't accelerate, it just rides a wave of compressed space-time. The problem is that this requires exotic matter with negative energy density, something we've never observed and may not exist. Even if it does, the energy requirements are astronomical, potentially more than the total mass energy of observable matter in the universe, depending on the design. Recent refinements have brought those estimates down somewhat, but we're still talking about amounts of energy far beyond anything humanity could harness in the foreseeable future. Wormholes face similar issues. They'd need to be stabilized with exotic matter, threaded carefully to avoid collapse, and positioned at both ends of the journey before you could use them, which means you'd still need to get to Andromeda the slow way at least once to set up the other end of the tunnel. None of this is impossible in principle. Physics doesn't strictly forbid it, but the gap between not forbidden and achievable is enormous. So if we can't visit, what can we do? We can observe, And with future telescopes, we may be able to do far more than just look at Andromeda's overall structure. Concepts like the Large UV Optical IR Surveyor, or LUVOIR, or the Habitable Exoplanet Observatory, HABEX, aim to build space telescopes with apertures large enough and optics sharp enough to resolve individual planets around stars in nearby galaxies. These wouldn't give us surface details, the planets would still be just points of light, but we could analyze their atmospheres using spectroscopy, look for oxygen, methane, water vapor, maybe even industrial pollutants or chlorophyll-like biosignatures. We might never walk on an Andromedan world, but we could, in principle, detect whether one of them has life, or had life, or built cities. Andromeda forces us to confront the limits of exploration. It's close enough to study in exquisite detail, close enough to see with our own eyes, but still impossibly far for any kind of direct contact. It's a frontier we'll cross with telescopes, not rockets, with data, not footsteps.
Part 7. Why Andromeda Matters. To most people, Andromeda is just a faint smudge in the autumn sky. Pretty, maybe, if you know where to look, but not particularly meaningful. To astronomers, it's something else entirely. Andromeda is the only large spiral galaxy close enough that we can study it in the kind of detail usually reserved for objects within our own galaxy. We can resolve individual stars in its halo. We can map its globular clusters one by one. We can trace the orbits of its satellite galaxies and measure the velocities of gas clouds in its disk. This level of precision is impossible for galaxies millions or billions of light years away, where even the brightest stars blur together into a collective glow. At the same time, we can see Andromeda's entire structure at once. We're looking at it from the outside, face on, which gives us a perspective we'll never have on the Milky Way. When you're inside a galaxy, it's hard to map its overall shape. You can infer structure from stellar populations and gas distributions, but you're always working with incomplete data, trying to reconstruct the whole from fragments. Andromeda lets us skip that problem. It's both close and external, a perfect laboratory for testing theories about how galaxies like ours form and evolve. Its stellar streams, for example, are direct evidence of hierarchical assembly, the idea that large galaxies grow by consuming smaller ones over time. Every stream in Andromeda's halo represents a dwarf galaxy that no longer exists, its stars now scattered through the larger system. The Milky Way has similar streams, remnants of past mergers, and studying Andromeda helps us understand what those features mean for our own galaxy's history. The supermassive black hole at Andromeda's core offers another point of comparison. It's significantly more massive than Sagittarius A star, the black hole at the center of the Milky Way, which raises questions about how black holes and their host galaxies co-evolve. Does a larger black hole mean Andromeda experienced more mergers, more gas inflows? Or is the relationship between black hole mass and galaxy mass more complicated than we thought? Andromeda's relatively low star formation rate is also instructive. Despite being larger and more massive than the Milky Way, it's forming stars at roughly the same rate or even slightly slower. This suggests the galaxy has already converted most of its available gas into stars, or that feedback processes, stellar winds, supernova shockwaves, radiation from the central black hole, have heated or expelled the gas needed to fuel new stellar generations. This phenomenon is called quenching, and it's one of the key processes that determine how galaxies age. Understanding why Andromeda is quenching helps us predict whether the Milky Way will follow a similar path and what that means for the long-term future of star formation in our own galaxy. But perhaps the most important reason to study Andromeda is simpler. It shows us our future. The Milky Way and Andromeda will collide. Not in the dramatic, explosive sense. Stars are so far apart that actual collisions between them will be extremely rare. But the galaxies themselves will merge, their gas clouds slamming together and igniting waves of star formation, their spiral structures distorting and eventually dissolving, their central black holes spiraling inward until they coalesce into a single, even more massive object.
The result will be a new galaxy, sometimes called Milkomeda or Milkdromeda, likely an elliptical or lenticular system rather than a spiral. By then, the Sun will be nearing the end of its life, swelling into a red giant and possibly engulfing the inner planets. Earth, if it still exists, will be uninhabitable. Studying Andromeda now is a way of studying that future. Every feature we see, the stellar streams, the warped disk, the traces of past mergers, tells us something about what the Milky Way will experience when its turn comes. It's also a reminder that the universe is not static. Galaxies move, they collide, they evolve. Nothing stays the same, not over billions of years. Andromeda matters because it's a mirror, a model, and a preview all at once. It's the closest thing we have to seeing ourselves from the outside. Every clear night, Andromeda rises, a soft glow just above the tree line, barely visible unless you know where to look. It doesn't blink, it doesn't move across the sky like a planet or flare up like a meteor. It just sits there, faint and constant, the way it has for as long as humans have been watching the stars. The light reaching your eyes tonight has been traveling for over 2 million years. It crossed the void between galaxies while early hominids were still learning to use stone tools, while the Earth turned through ice ages and warm periods, while entire species rose and fell. That light traveled alone through the dark, carrying information about a galaxy as it existed in the deep past, and it ended its journey here, absorbed by the cells in your retina. You're seeing history, not metaphorically, literally. The Andromeda you observe tonight is a ghost, preserved by the finite speed of light. And while you've been looking, Andromeda has been moving. Not away, like most galaxies in the expanding universe, but toward us, closer with every passing second. The gap between the Milky Way and Andromeda shrinks by about 110 kilometers every second. That's too slow to notice in a human lifetime, or even in all of recorded history. But over billions of years, it adds up. The collision, when it comes, will unfold slowly by human standards. The galaxies will pass through each other, their stars scattered into new orbits, their gas clouds igniting in bursts of star formation. They'll swing apart, then fall back together, merging and reforming over hundreds of millions of years, until eventually there's just one galaxy where there used to be two. By then, the Sun will be dying. The Earth, if it hasn't already been consumed, will be a lifeless cinder. But the matter, every atom that was ever part of this world, will continue, drifting in space, locked inside new stars, recycled into forms we can't imagine. The universe doesn't erase things, it just rearranges them. Andromeda is a reminder of that, a reminder that nothing in the cosmos is permanent, that even galaxies have life stories, that distance and time are not barriers to connection, but just parameters in a much longer process. We can't visit Andromeda, not in any physical sense, not with our current understanding of physics, but we can see it, we can study it, we can map its structure, trace its history, predict its future. And in doing so, we learn something about ourselves, about where we came from, what we're part of, and where we're going. Tonight, if the sky is clear, you can step outside and see it for yourself. No telescope required, just dark skies and patience. That faint smudge above the horizon, it's not just light. It's a neighbor on a slow, inevitable journey toward us. 1 trillion stars, countless planets, and a future already written in the equations of gravity. It's coming home. Thank you for spending this time with Andromeda. If this journey shifted something in how you see that faint smudge in the sky or made you think about galaxies differently, I'd love to hear your thoughts in the comments. Do you think we'll ever find a way to bridge the gap between galaxies? Or is observation the only voyage we're meant to take? If this video gave you something worth thinking about, a like helps the channel continue. Subscribe if you want to keep exploring the quiet corners of the cosmos where distance meets time and where every answer leads to deeper questions. The universe doesn't make itself easy to reach, but it's always there, waiting for anyone willing to look up. See you in the next one.